Welcome to the course of finite element method. This course is all about a numerical method applied to different domains of engineering, not limited to mechanical engineering, structural engineering. It is expanded and can be exported towards the electrical and other core domains of engineering. So now in this course or in this short video, we will discuss about shape functions and their significance. What is a shape function? Shape functions are mathematical functions used to approximate how a physical quantity is like displacement, temperature, pressure varies inside an element. And basically, a shape function is something like finding something which is between the two elements or 2 points like this. Say for example, we have an object like this, and this point, let us say this is x1 and this is x2. I want to find out the midpoint of x1 and x2, so it will be somewhere like this. So how do you find that? So this is x1 plus x2 by 2 happens to be the midpoint of this particular straight line. When you see this, so this is, we can write like this as an 1 by 2 times of x1 plus 1 by 2 times of x2. So when we are writing 1 by 2 of x1, 1 by 2 of x2, which indicates that they are all the weight functions with respect to the coordinates of x1 and x2, which are positions. So from this, for example, if I want any point between x1 and x2, for example, so I have a point somewhere here. So hence, say let us say this distance this is 1 by 5 and this is the other distance is 4 by 5. So then we write this as 4 by 5 times of x1 plus 1 by 5 times of x2. So this is how we write the shape function, and this defines, it is basically called as an interpolation function, which takes the care of the nodal values to any point within the element, and it is usually denoted by ni of xi. So for a one-dimensional element with the 2 nodes, it was written like this, because when we see here in this diagram, we have seen x1 and x2 are the two extreme points. Then we write this as 1 by 2 of x1 and 1 by 2 of x2. So when we see this, when I want, we'll move to the next slide. Say for example, when we have an object like this, line of x1 and x2. Now what we have, if we have a point here like this, so this we have something like x1 plus x2 by 2 happens to be at the center. This is let us say this as case 1. So coming to case 2, we have, let us assume we have something like a point. So this point, if you want, which is 1 by 4 of the distance, say let us say this is 1 by 4 and this is 3 by 4. So this we write it as a 3 by 4 of x1 plus 1 by 4 of x2. So vice versa also, let us say take this as a case 3, where I can write this as an 1 by 4 on this side and 3 by 4 on the other side. So we can write this as an 1 by 4 of x1 plus 3 by 4 of x2. When you see this, whatever the values which are coefficients of x1, the coefficients of x1 are always between the limits 0 to 1. So hence the value of this shape function ni 1 to 1 to 0 is, so the value of shape function is equal to 1 at the respective node, and at other nodes it is equal to 0. So in this connection, what we'll try to do is, we'll try to develop a shape function, and how it is going to change, it is how we formulate it. So the next one is the sum of the shape functions is equal to unity, and we'll try to do that. So that is what we have seen, that is 1 by 2 of x2 plus 1 by 2 of x1, or we can also write this as x2 plus 0 of x1, which is at node 2, and this is at a midpoint And similarly to the other one, so we can write this as 0 and that times x1, which is at node 1. So the idea here is the value of shape function is like this. Now let us say, let us take an element like this. This is first node and this second node, and this we call it as an element. And the shape function is written like this. The value of n1 is equal to 1 or ni is equal to 1, and it is happens to be 0 like this. Similarly, when we take another one where the shape function is like this, where it is equal to 1 at node 2 and it is equal to 0 at this point like this, and here this is this n2 is equal to 1. Now the line which is describing this blue line is a shape function. Similarly, this red line, both are indicating the shape functions. These are all indicating the shape function. Now if we take this shape function as linear, then how do we write that? So any shape function, if you want write a function which is having 2 points, here n1 is equal to 0 and here n1 is equal to 1. We have 2 points here, where for a local coordinate system we take xi is equal to -1, we take xi equal to +1 for this. So let us take the shape function is in the form of a0 plus a1 xi, which is a function which is representing the red color function like this. This is this, which is represented as f of xi. And this is what this is also called as this shape function, which is n1. Now when we substitute the value of xi at 2 points, n1 is equal to 1 at xi -1, which is at node 1, that is node 1, which is we can write, when we substitute it, it is a0 minus a1 is equal to 1. And similarly we have, when we do it for node 2, then n1 is equal to 0 at xi equal to +1, that is at node 2, and then it becomes a0 plus a1 is equal to 0. Now taking these two equations, when we solve it, we have something like a0 is equal to 1 by 2 and a1 is equal to -1 by 2. So hence the shape function looks like this, as we write this as n1 is equal to a0 plus a1 xi happens to be 1 by 2 minus of 1 by 2 xi. In the same way, when we solve for n2, then it looks like n2 is equal to, let us say, call this as n b0 plus b1 xi. Upon solving this, what we get is b0 we get 1 by 2 and b1 as 1 by 2 xi. So n1 and n2 are the shape functions, as we have made in the previous slide. It is like this, where this is taking that part, and this is the first equation, which is n1, and the next one this is n2. So when you see here, this is in the form of a linear expression, hence the variation of this shape function is linear. So this happens when the numbers here are 1 and 2. So here 1 and 2 are representing the nodes, and if only 2 nodes are there, then this is called as an one dimensional 2 noded element. So this we call it as one dimensional two noded element. Okay. Now when we are doing this, so this is one dimensional two noded element which is represented as in the local coordinate system. Now look at this, the other aspect here. When I am taking a different setup altogether, here this part, this equation, what I am trying to see here, it is starting here and the end point is 0, which is this line is basically a straight line. Now if I want to convert that into a linear form or a non-linear form, then the variation will be different. So then this is happens to be a non-linear function. This is called as a non-linear function. For that, what we need is, if more than 2 points are there, then we have to go for non-linear shape function. So whatever we have discussed till now, this is all about two noded one dimensional element generates only a linear shape function, which are these two. The first one is this one and this is the second one. Now why these shape functions are important is, shape function, if you see here, they are varying very linearly, either it is n1 or n2, they are dependent and are linear in a functional order. Okay, first order for functions. Next is, when we have these shape functions, then these shape functions, if at all they are for two dimensional or quadratic shape functions. One second. Now before we go to this, from this we understand, if you know the values of the corners or vertices, we can estimate the value inside. For example, the outcome of this is, say for example, we have an object like this as an x1 and x2 like this. I have the coordinate this as 3 and this as 4. I want somewhere here, so I can find out if this is this point, I can write 1 by 2 of 3 plus 1 by 2 of 4. That gives, it is happens to be 3.5. It is if it is at the center. So for any values of these two coordinates of 1 by 2 varying between 0 to 1 only, and it means that the limits of the shape function are between 0 to 1 only, which means that the value of shape function is equal to 1 at the respective node, and other nodes it is equal to 0. This is called the importance of the shape function, which is called unity. The sum of the shape functions is equal to 1, which we call it as an unity of the shape functions. Now we'll discuss that with respect to the other two-dimensional case. So far what we have discussed is, we have discussed about x1 and we have discussed about x2. Right, only 2 points are there, which happens to be the nodes of the element. We have something like this, which is having the 3 points, which is x1, this is x2, there is a midpoint which is x3. Now for this one we already defined that n1 is equal to 1 minus xi by 2, n2 is equal to 1 plus xi by 2. In this case, here how we have to define for this function, the same thing here. I repeat again, this shape function, as we have discussed it for the for this one, the value of shape function is equal to 1 for this and equal to 0 here and equal to 0 here. Now the shape function value here, this n1 is equal to 1 and equal to 0 at this point and equal to 0 at this point also, right? Similarly for the other one, for example, we take the other function which is like this, where this value of this is equal to 1 at this point, which is n2 is equal to 1, is 0 at this point and also like this. Okay, so sorry, I'll try to correct it here, and n2 is 3. Now similarly for a third node, it is like this. The value third node have unity value at the at that particular point, at other nodes it is 0. So from this we understand that all the shape functions which you are seeing in this are not linear. They are not linear.
Whereas in the first case, when we have drawn like this, and they happen to be the linear case, right? But here it is not linear. Hence, if 3 points are there, then the safe function n or n of xi, we write this as a naught plus a1 xi plus a2 xi square. Okay. Now, the same thing what we will try to this we will apply for all the 3 points, and then we finally we calculate or we find the safe function. So we move to the next slide to mention this, that is n of xi is equal to a naught plus a1 xi plus a2 xi square. Now at node 1 xi equal to -1, at node 2 xi equal to +1, at node 3 xi equal to 0. Okay. From this we have a safe function which is I'll call this as an n1 xi, which is a safe function for the first node starting at node 1, is equal to 1 at node 1, equal to 0 at node 2, and equal to 0 at node 3. Okay. So how we will write? Please look at here. So at node 1 the value is xi, so we will write this as an a naught minus a1, where we are substituting xi is equal to -1 in this expression, plus a2 equal to 1. The second expression is a naught plus a1 plus a2 is equal to 0. The third expression is where it is equal to xi equal to 0, a naught plus 0 plus 0 is equal to 0. So solving these three equations, we can find out what is a naught, a1 and a2, and where here a naught is equal to 0 and a1 is equal to -1 by 2 and a2 is equal to 1 by 2. So hence the safe function n1 of xi for this particular node happens to be minus xi by 2 plus xi square by 2. The same approach when we do it for the second node, it happens to be n2 of xi. When we solve it, these equations, the similar equations which happens like this, like a naught minus a1 plus a2 is equal to 0, a naught plus a1 plus a2 is equal to 1, a naught plus 0 is equal to 0. So hence again this gives us the expression that a naught again is equal to 0, okay, and a naught, a1 is equal to 1 by 2 and a2 is also equal to 1 by 2, and hence this expression happens to be xi by 2 plus xi square by 2. Okay, and the same way for the third one is like this. I'll be taking it in the other side of this next slide. n3 of xi, we write that as an a naught plus a1 xi plus a2 xi square. So we can take another form that when xi equal to 0, what happens? So the first one is a naught plus a1 times 0 plus a2 times 0 is equal to 1. At -1 it is a naught minus a1 plus a2 is equal to 0. At z equal to +1 it is a naught plus a1 plus a2 equal to 0. On solving all this, we get a naught, is equal to 1 and a1 equal to 0 and a2 happens to be minus 1, and hence this function n3 of xi happens to be 1 minus of xi square. So to summarize, what we have here is, for one dimensional two noded elements, what we have here is, that is, and when element is like this 1, 2 and this is an element, then the shape functions are n1 of xi is equal to 1 minus xi by 2 and n2 of xi is equal to 1 plus xi by 2. But when it comes to same one dimensional three noded element, it happens to be this 1 and this is 2 and maybe this is 3. So we write it as an n1 of xi is equal to minus xi plus xi square by 2 and n2 of xi is equal to xi plus xi square by 2 and n3 of xi is 1 minus xi square. So from this we understand that z functions are the values which are deciding the variable position and how the variation of the field variable like displacement, temperature and all these are all dependent on these equations. If you want the variable to vary linearly, we will take two noded element. If you want the variable to vary quadratic form, then this three noded element will cater the purpose. Similarly, for higher order elements, then the shape functions will keep on increasing. So for example, if at all, if it is a two noded element, the shape function, for a two noded element, the shape function is n of xi is represented as a naught plus a1 xi. For a three noded, the similar shape function is represented in the form of a naught plus a1 xi plus a2 xi square. The four noded element represents similar function, which is in this form a naught plus a1 xi plus a2 xi square plus a3 xi cube. Now when I say two noded, it is a linear element. When it is a three noded, we call it as a quadratic element, and when it is a 4, we call it as a cubic element, and similarly 5 and 6, they are all called as higher order elements. So with this, we say that the shape functions are very much important in case of the finite element modeling methods. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.